It's my pleasure today to introduce our first speaker, Dr. Joseph Ponnoly, talking about digital twins and cybersecurity. Dr. Ponnoly is a researcher within the community, and as you can see, has a lot of accolades and accreditations within the space. And so this is a very interesting topic to myself, and I'm really looking forward to hearing this speech. And so without further ado, Dr. Ponnoly.
Good morning, everyone. So my association with digital twins and OT security is more from the research point of view, though I worked with Chevron earlier, and I have been dealing with OT security also. So today I'll be dealing more with industrial digital twins. So how many of you are familiar with the concept of digital twins? How many are working with digital twins? Great, okay. So as he said, I'll focus more on industrial digital twins, the applications of digital twin technology for manufacturing and the industrial sector, particularly in the wake of the Industry 4. As you know, Industry 4 opened up OT, operation technology, to the internet, and that brought in a lot of security vulnerabilities and a lot of cyber attacks. We'll deal with some of those cyber attacks and what are the risks by opening the industrial control systems, the security of that. So digital twin is actually a layer above the industrial control systems and SCADA systems. So an example of a digital twin at the personal level, so you all have used Google Maps, right? So Google Maps is not fully a digital twin, but it contains the foundational elements of digital twins. So the best example from the personal point of view of a digital twin is the fitness, the wearable devices, the Apple Watch. That is a good example of a digital twin. We'll go into details of what is a digital twin. So what I will try to do is, since you are already familiar with the concept of digital twins, I will just skip over some of those. But again, I will try to go into the fundamental concepts. The digital twin, focus more on the key technologies and the key application areas and use cases, and then focus more on the security aspect of digital twins, the security breaches and the risks, and what are the countermeasures, and what are the regulatory guidelines and the standards that are applicable to digital twin technology. And then I will give an overview of a case study of using digital twins for monitoring cybersecurity black swan events. Black swan events are the unexpected cyber events, the unexpected, unpredictable cyber attacks. So can we use digital twins to secure our operational environments, the industrial control systems, manufacturing, the aerospace, or wherever security, digital twins can be applied. So three areas I'm focusing on: the digital twin concepts, then security of digital twins, and using digital twins to secure industrial control systems. So what is a digital twin? So this concept is attributed to Dr. Michael Greaves from 2002. He worked at the University of Michigan. He was focusing more on product lifecycle management, from the conceptualization of the product, design of the product, to manufacturing implementation, and more on the operational management, safety, and maintenance of products. So what was being done was to physically inspect the products or installations and identify, measure various parameters, temperature, pressure, fluid dynamics, and then identify where are the safety issues and how long the product will survive, what would be the life cycle of the product. So he suggested creating a virtual replica of the physical product. And that was later on, it caught the attention of NASA. And from 2010, NASA has been employing this concept of digital twin. So there is a difference between a virtual replica and the digital twin. So what differentiated digital twin from a virtual replica of a physical system is the data flow. The data flow can be one way, then it is called the digital shadow. A digital twin has a data flow back and forth. So you get various sensors measuring the various parameters of the physical environment. And then you can do simulations and you can do monitoring and then give feedback to the system automatically to correct the position. So digital twin is a virtual model of the physical asset or process. It's the digital replica, and it enables real-time monitoring. So real-time monitoring, simulation, and optimization. So simulation and optimization, these were the additional aspects of digital twins, differentiating that from the industrial control systems or the SCADA systems. So the normal question asked is, what is the difference between the digital twin and the ICS, industrial control system, or the SCADA system, the supervisory control and data acquisition systems? In fact, it is not, digital twin doesn't duplicate the functions of the ICS or the SCADA systems. It is complementing that. It is adding a layer, additional layer to this for better optimization of the process. So that's simulation part of it. That is not done by the PLCs or the SCADA systems. They just take in the parameters from the operation environment, and then it controls the industrial processes. It doesn't optimize. It doesn't it does continue monitoring, but it may not be real-time monitoring. So that simulation part of it, optimization. So optimization part, that is the major advantage, the cost advantage. So instead of physically going and inspecting the whole refinery, having various components of it, creating a virtual replica of it, simulating the environment, and doing various what-if analysis, that is the real advantage of digital twin. This concept was not new to NASA. I mentioned that NASA has been using this for aerospace sector from 2010 onwards. But you know the Apollo 13 disaster in 1970, April 13, 1970, the Apollo 13, that mission that failed, and they aborted the moon landing mission. Then it happened because of the burst of the oxygen cylinders, and then there was power failure and buildup of the carbon dioxide and carbon monoxide, so endangering the life of the astronauts. So at that time, what NASA did, Mission Control did, they had a physical replica of the command module and the service module, and then they recreated the various parameters for safety, the temperature, pressure, the oxygen levels, carbon monoxide, and then they were constantly in communication with the astronauts to see how to use whatever they had. So they used duct tapes and all that to seal off the leaks. And finally, they were able to simulate that. So a simulation environment was created physically, and then they were able to safely land the astronauts back to Earth. So they're creating the virtual replica of a physical system. When the physical system is not easily accessible, that is the main advantage of a digital twin. So the key components of a digital twin. So you have the physical entity, the real world object, the system or process. So digital twins are now used not only in the industrial control environment, manufacturing environment, it is also used in the financial systems. So HSBC, they are using a digital twin to monitoring the processes, because processes are complicated. There is a lot of movement, the behavior of the customers that is changing. So they are using that also for financial digital twins. So we'll come to that, and for fraud detection and so on. So now we are focusing more on the industrial sector. So you have a physical entity, then you're creating digital model, the virtual representation. So the 3D models, it could be the 3D models. Now with metaverse, 3D modeling, that has become important. So metaverse is being used. Then simulations and analytics, the data connectivity. So you have real-time data connectivity. So you are using edge computing or cloud computing and the various communication protocols, where it is MQTT or UPC, UA or HTTP. So various communication protocols, Bixby and so on, they are used for collecting the data collection, and for ingestion of the data, and for analysis. For analysis now with AI, data, machine learning, and so real-time analysis of this data, that has become important. So data connectivity, analytics, and the various AI, machine learning algorithms, and then the feedback mechanism to apply the insights from the data to the digital twin, from the digital twin back to the physical entity for correcting course correction. So these are the key components of digital twin. Coming to the tools and technologies that are used. So you have the physical object, and sensor technology, the IoT platforms, they have become important. So IoT platforms, they collect the data. So the sensor technologies are used, and then you have various middleware, like integration middleware, for like event monitoring software like Apache, Kafka, and then you have the digital twin modeling tools and technologies. Like CAD software has been used since time immemorial. So various simulation tools and 3D visualization platforms. Data analytics and integration middleware. These are very important from the digital, implementation point of view. So basically you create a virtual model. So modeling is important, how well you are capturing, creating the model of the physical object. That is the crux, the major challenge in creating a digital twin. Then using various data analytics platforms, machine learning and so on for analytics, and then giving the feedback back to the physical object for correcting these objects. So various technology vendors, they have created digital twin platforms. So the cloud providers, Microsoft Azure and Amazon Web Services, they have the IoT and digital twin platforms. Siemens, General GE, and Schneider Electric and so on. The Philips, even for medical devices, Philips, they have their own digital twin platforms. So digital twin technology is gathering momentum. So these platforms are used for various industrial applications, manufacturing applications, and wherever a digital twin is now being applied, from transportation, aerospace, even defense, to even the financial sector. So the key application areas, so industrial manufacturing for predictive maintenance or process optimization. Now supply chain management, that is another important area because of the disruptions in supply chain with all these tariff changes. So supply chain management is very important for industries to identify the various parts which go into the manufacture of various industrial products. Aerospace and defense, as I mentioned, aircraft performance modeling, and defense for simulation. So simulation for war game that has been done by various agencies. Automotive and mobility. So autonomous vehicles, they are using a digital twin even for fleet management. Now, smart cities and urban planning. So traffic management, infrastructure monitoring, and for energy efficiency. These are being used. Healthcare, again, is using digital twins for personalized medicine, surgical simulations, and hospital operations. Typical industry use case, so Boeing aircraft, it uses digital twins for their manufacturing of the new planes. Lockheed Martin, for example. Siemens, they have digital twin smart factories. Tesla is extensively using digital twin concept. Singapore is creating a virtual smart city in Singapore using digital twin technologies. And GE has got its digital wind farms. So these are some of the industry use cases for digital twin. Now, with advancements in artificial intelligence, AI technologies, machine learning, reinforcement learning, now generative AI, LLM. So AI is being extensively used for digital twins. So the popularity of digital twins is mostly because of the advancements in AI, IoT technologies, sensor technologies, and as we see, even metaverse, 3D dimensional applications of digital twins. So using AI, you can use predictive analytics for AI-powered models, creating the AI models. So proactive decision making. Digital twin, ultimately, it is a decision making tool. That is the power of digital twin. It helps decision makers to make effective cost-effective decisions to optimize on the cost and efficiency of various machineries, industrial products, and so on. So big data, advancements in big data. So dealing with unstructured data instead of the traditional structured data, creating data lakes. So big data processing, Hadoop and Hadoop systems and so on, they have actually accelerated or enhanced the capability of digital twin technology. AI-based anomaly detection that helps in identifying various safety issues in various industrial environments. Deep learning and reinforcement learning and LLM technology, generative AI. Now, again, with advancements in automated AI agents. So these help in not only simulations, predictive analytics, so in simulations particularly, autonomous operations, self-learning, and AI-driven control in manufacturing and energy systems. So LLMs for prompt, you can use prompts to query the system on how it can be used for better efficiencies. And for complex systems, AI is particularly useful for complexities. And distributed learning, federated learning, wherever privacy is involved. So federated learning is for privacy protection. So there, again, AI is extensively used. So use of AI and advancements in artificial intelligence, that is enhancing the capability of digital twins. Metaverse, again, is another technology. So the augmented reality or virtual reality systems helping in 3D visualization. So AR, VR integration with digital twin, that helps in enhancing the capability of digital twins. So it helps in multi-user collaboration, and of course IoT and edge computing, they can be used for reducing the latency of processing. And it helps in simulation, AI-driven simulations for predictive analytics, for optimized operations. Another technology that is now being used is blockchain technology, because blockchain for data integrity of data. Data is the crux of digital twin. If you don't have real data, that is trustworthy data, then whatever simulations you do, that is garbage. So to see that data is trustworthy, the integrity of data is ensured. So blockchain technology is currently being used. Now coming to the cyber security of this digital twins. What are the security vulnerabilities? What are the security implications? What are the risks? And how do you mitigate those risks? Security of industrial control systems, you have the well-known incident of the Stuxnet attack on the nuclear centrifuges of Iran. So that was the malware, zero-day exploit malware that was used to attack or to disable the Siemens PLC in these centrifuges, and that disrupted the operations, and it was almost a cyber war, and that against Iran, orchestrated by, of course, US and Israel, and that was very successful because they were able to disable the PLC, Siemens PLC. And that is the well-known incident which exposed the security of industrial control systems. So GE predicts, I've mentioned that GE has got the IoT platform called Predix. So it has very many vulnerabilities of this Predix system. They were exposed in 2021. Similarly, Siemens has got the digital twin platform called MindSphere, and that also, there were a lot of vulnerabilities which were exposed. And Schneider Electric system, that was actually attacked, and that is one of the famous cyber security incidents of 2017 in Saudi Arabian petrochemical complex. So the Tritron Trisis malware was used to attack the Schneider Electric system. It was the digital twin system in the Saudi petrochemical complex. And fortunately, the SIS, the safety control mechanism, that was able to identify the anomaly and shut down the system. Though this complex, it became non-operational for a number of days, it was able to save the lives of the human beings. That was where this this system, the existing security system, industrial control system, the SIS of Schneider Electric. Schneider Electric, you know, is the French company. So that was able to save the company. If they had succeeded, actually the attack came from, it was initially thought that it was attack on Saudi petrochemical complex. It was suspected, Iran was suspected in the attack, and later on FireEye, they were able to do the forensics, and they were able to identify that it was done by Russia, and Russia had got had a research institute just developing these technologies for cyber attacks, these cyber weapons. They are cyber weapons. In fact, they were in the system for almost 3 years, from 2014 to 2017, before the attack took place. So that is this Schneider, the attack on the Saudi petrochemical complex. That was a major security breach. Then there has a Tesla factory itself was disrupted. Their digital twin was attacked, and that was an insider attack. The insider, the disgruntled employee, stored the source code, and then that was used for the attack. So insider security, insider threats. So that is something which we cannot ignore. and smart city implementations also in Barcelona and India. There were also some attacks on these systems. So what are the major security challenges? So digital twin, as we saw, it uses a whole lot of technologies. So the attack surface has expanded. So they are interacting with the physical systems, the cloud platforms, the edge computing, then the sensor technologies, then there are the AI analytics engines, and then if we are using blockchain or even metaverse, so all these technologies and platforms, they have their own vulnerabilities. The attack surface has expanded, making it easier for cyber attackers to penetrate the systems, then remain undetected and use what is called the advanced persistent threat attacks, remain low and then explode after a certain time. They create backdoors, elevate the privileges, move laterally, elevate the privileges, and take control of the systems and then explode. So the attack surface has expanded. The edge layer, device layer, communication layers, so the various communication technologies that are being used, they have their own vulnerabilities. Then the data layer, which is mostly ignored, the data quality, so the possibility for data poisoning. All these are various issues which have to be considered from the security point of view. The application layer, now OT, we have opened it up to the internet, so the OT, IT, web interfaces, the various APIs which are being used for connectivity. All these have their own vulnerabilities, and these are part of the security challenges. Then the data part of it, the data infrastructure, that is critical to the security of digital twins, because we are doing real-time, using real-time sensitive operational data, and that has to be protected. So for attackers, earlier, instead of attacking a petrochemical system or a refinery or industrial manufacturing system, now they can attack the digital twin, which is simulating the environment and controlling the environment. So that it makes it easier for attackers to attack the digital twin. So security of digital twin is critical. So there, the model, certainly the modeling part of it is very important, but the data which is used for the monitoring and simulation and feedback and control, so quality of the data, integrity of the data, that is critical for security, and that is a major security challenge. So leakage of unauthorized leakage of data, unauthorized access. So access control is also equally important. That's why zero trust has to be implemented in industrial control systems. Zero trust. Trust none, verify everyone. So integrity of simulation control functions, the machine learning algorithms, they can be poisoned. There is adversarial attack by attackers on the machine learning algorithm itself. Insider threat, as happened in Tesla, that is of concern. Supply chain and software dependencies. So NIST is now focusing on software security, because software is at the heart of every system, including industrial control system and digital twin. For Tesla, the automated car, it has got over a million lines of software code. Just imagine where it is possible to identify the software vulnerabilities. So NIST now wants every software that is used, the bought out, particularly the third-party components, the software bill of materials, that must be listed. So I was doing a security assessment for a medical device, and to submit for FDA approval, and it was found that though the manufacturer mentioned only 2 or 3 software components, ultimately take into consideration all the open source components used, the libraries which are used, it was found that nearly 400 nearly 400 different software components were there, and they had their own vulnerabilities. So supply chain, software dependencies, software vulnerabilities, these are all security challenges to be considered. Specifically about the risks, the security breaches and cybersecurity attacks, they focus on the sensitive data. That is the prime target for attackers. So that can lead to operational disruptions and theft of proprietary information. So insider threats is a security risk. So anybody dealing with defense protection. Now you know that CMMC is CMMC, that is mandatory for those who are supplying supplying to the defense department. So capability maturity model for defense purposes, CMMC model, that compliance is highly rigorous for the controlled unclassified information that is being used for in the various products that are supplied to, or services which are supplied to the defense. Machine learning risk, so manipulating the algorithm itself, the AI-driven digital twins, so that can lead to incorrect predictions and operational failures. IoT and network vulnerabilities, IoT devices for real-time data collection. Then the privacy concerns, so you have to comply with GDPR, CCPA, HIPAA, and so on. Some of the regulatory frameworks which give us guidelines for securing these digital twins. So NIST has got the various standards for zero trust architecture, then for IoT device cybersecurity, so NIST has got its own standard. System security engineering for security by design, and then NIST has got this NIST cybersecurity framework version 2, which was released in 2024. So that helps in incident management, how to have a proactive approach to incidents, and then after an incident happens, how to control, contain the incident and the impact of the incident, and how to recover from it. ISO has got its standards, so the ISO 27000 series for information security management. Then there is a smart city standard concept model. Digital twin framework for manufacturing, so ISO has got 23247, that has got a reference architecture and various security attributes which map to the IEC and ISA standards. The industrial control system safety and digital factory standard, that's also there for ISO. The European Security Agency, ENISA, they have given their guidelines for secure IoT and smart manufacturing. So Industry 4 is focusing on smart manufacturing. So those guidelines for Industry 4. And ENISA also has got guidelines for AI security. Now, as you know, European Union has got its own legislation, the European AI Act, which is very rigorous regarding products which have an AI component. The FDA in US for medical devices, they have very stringent standards for certification programs. So medical device security, the threat modeling, the risk management, and then as I mentioned, the software bill of materials and so on. So it has got very detailed guidelines on medical devices and digital. Yeah.
Dr. Ponnoly, you mentioned, SDLC, software development lifecycle.
Yeah.
IEC 62443, sections 4.1 to 4.3 deal directly with SDLC.
Okay. Okay. Thanks for pointing it out. Okay. So MITRE standards, the MITRE framework, that is particularly useful to understand the various techniques which are used by cyber attacks. So it is constantly being updated. So from reconnaissance, so what are two final attack, as I mentioned, the APT, advanced persistent threat attacks. The attackers enter, lie low, then they lie low for months or even years. So in the SolarWinds hack, which happened, they they remained low for nearly 8 to 10 months before they attacked the supply chain. So MITRE framework is also particularly useful for securing this. So how do we secure the digital twins? What are the focus areas? So data transmission, secure data transmission. So encryption technologies. So integrity checks. So encryption now with quantum computing, which is almost on the horizon. So we have to think of post-quantum cryptography that is already being used. It has to be implemented. The post-quantum cryptography standards from NIST, they are already to be used, because what attackers do, like those in Russia, North Korea, the major attackers, so they are downloading even encrypted communications from critical infrastructure sectors, so that when quantum computing is already is operational, they can use that encrypted communication to decipher the encrypted communication, and which may be very sensitive from the national defense perspective. So what the government of for the government and NIST, they require is wherever encryption is used, you have to use a post-quantum cryptography standard. So secure data transmission is very important. IoT security cannot be ignored. So device authentication, device-to-device authentication, single sign-on OAuth protocol. So instead of just using, so device authentication is very often ignored. Default passwords, user IDs and passwords are there in hard-coded in many of the devices, even from reputed vendors. I don't want to mention some of them because we found them. So device authentication and firmware updates, these are very important, because many of the products which are coming from some of these adversarial nations, particularly China, you find that firmware is already corrupted. They have trojans in the firmware. So we found some of the drone software having firmwares with corrupted backdoors. Access control cannot be ignored, so zero trust implementation has to be implemented, multi-factor authentication. The physical security is also important, and for cyber physical security, we have to anomaly detection that can help. Then blockchain integration for data integrity and compliance, these are also cannot be ignored. So now let's just to see how these concepts can be used in a case study. So it is using digital twin for monitoring a system, industrial control system for particularly relating to cyber black swan events. So again, just to refresh, digital twin definition is a real-time digital counterpart of the physical system or network. We are using it for simulation, monitoring, prediction, and optimization. What is a cyber black swan event? It's a rare, unexpected, unpredicted cyber events. So we had the Stuxnet was a cyber black swan. They never expected it. SolarWinds hack or NotPetya, WannaCry. These were all cyber black swan events. So in this model, we are trying to predict the cascading effects of cyber attacks and identify the weak signals. Even for cyber black swan events, there could be weak early warning signs which are either ignored or they are missed. In fact, my doctoral dissertation was on cyber disasters. And so we also need to stress test the system for system resilience. That is for even if an attack takes place, the impact is minimized because you already have a backup. You have a plan B backup systems for continuing the operations. So black swan use case, I mentioned supply chain attacks as in SolarWinds, so zero-day ICS exploits, cloud breaches, and disinformation, AI-driven disinformation. So just a high-level architecture of what we are trying to do. So we have the physical system. It could be IT, OT, or IoT, or the cloud systems, and there is continuous data feed. So we have to have a data acquisition layer. So we have the interfaces, so the IoT hub or whatever Microsoft Azure IoT hub. Then the APIs, then we have to capture all the security logs, then the network data pipelines and so on. Then we create a virtual replica of this system, a dynamic model mirroring the real world system's behavior, its components, characteristics. Behavior is important, and structure and the various dependencies. And then the simulation engine, it will emulate the attack vectors and the system failure modes and the propagation. And then we have the AI-based analytics layer to assess the anomalies and simulate future scenarios. And then we have the visualization dashboards. So the tools which can be used for simulation, we have various simulation platforms. And CyberRange is an important component of it. CyberRange, like IBM Expose, they actually simulate the attack models. So IBM Expose and Amazon Cyber Labs. So they provide a controlled environment to test the attacks, to almost do red teaming and penetration attacks on a simulated system. So a CyberRange can be used. And then you can also interface this with the digital platforms like Azure Digital Twins, or depending on the application area, Siemens or ANSYS Twin Builder. These are some of the digital twin platforms for real-time monitoring and analysis. So here, what is important for when you create a cyber monitoring system using digital model or any model is to do the threat modeling. So Stride is Microsoft's threat modeling framework. So you consider spoofing, the impersonation, or repudiation, deletion, the tampering, then the information disclosure, leakage of sensitive data, denial of service or disruption. So what is testing the system response under various denial of service attack mechanisms, and whether elevation of privilege is possible, and how. So threat modeling is done, and then real-time monitoring. For real-time monitoring, you have to integrate this with SIM tools like IBM QRadar or Splunk for monitoring the events. Then the threat feeds, so threat monitoring, the threat landscape is continuously evolving, changing, so you need to have a continuous threat intelligence feeds for real-time intelligence. And then the net flow, the data flow from the systems that has to be done using various net packet capturing data. And then the twin has to be updated, automatically refreshed as new data arrives. So this is a high-level model of this. So you have the SCADA and safety instrumentation system, the ICS control system. So just think of the attack on the Saudi petrochemical complex. So on the right side, that was what was happening. They attacked the safety instrumentation system. So if we now imagine you had a digital twin to support this, to monitor this, could it have prevented this or identified or detected this attack and prevented or stopped the attack? So you have the digital twin with real-time simulation, anomaly detection, and monitoring of the flows between the system and the digital twins. So digital twin should be able to capture using the anomaly detection, or if they had the integrity checks for various systems like tripwire and so on, then they could have identified there was an attack. So the software was being changed, the PLCs were being changed. So then the digital twin will be able to identify this and then in real time send alerts to correct the system. So I am short of time. So this can be enhanced using metaverse and with quantum technology, we can have quantum simulation, and agentic AI is the next technology or the technological advancement in AI. All these can help in. So summarizing this, digital twins are getting widespread adoption in manufacturing, healthcare, energy, transportation, aerospace, defense, and even in financial services. So a lot of technologies, AI, IoT, sensor technologies, cloud computing, edge computing, big data computing, metaverse, blockchains, they can enhance the capability of digital twins. Agentic AI and quantum simulations further can enhance digital twin technologies. We must secure digital twins. At the same time, digital twins can be used for cybersecurity. Thank you.